So hello everyone, thank you for coming in. Today we have Sean Papay in to tell us about his ICLR paper, Constraining Linear Chain CRFs to Regular Languages. Sean is a PhD student at the University of Stuttgart, working mostly on structured prediction, if I remember correctly. And now we're going to let him tell us about his work. So thank you for coming in.
And thank you for inviting me. So yeah, I'm Sean, as was already mentioned, and I'll be talking about this work, Constraining Linear Chain CRFs to Regular Languages. This is from ICLR of this year, and yeah, let's get into it. We have some time, so I'll try to go a bit slow and give a bit more background, then I'll try to give a bit of background. So let's start by just talking about what CRFs are. It stands for Conditional Random Field, but the acronym doesn't really tell you much. So I'll just give some examples. So we're going to talk about sequence labeling. And first, let's talk about how we would do sequence labeling if we didn't have a CRF, if we're just using a very kind of basic model, maybe a feed-forward neural network or something. So in that case, we would have a bunch of inputs, x's, they form a little sequence. And we have a bunch of label variables, y, and we want to assign one label to each x. And so in a typical non-CRF model, our model might look something like this. Where basically, if we want to predict the second label, we look at the second input representation, and we have our model approximate this distribution, P of y2 given x2. So that's not to say that this second label can't depend on anything else in the input. Maybe these input representations come out of, I don't know, for example, BERT. So maybe these input representations do have information about each other, and there is some contextual information within here, but at the end of the day, when you're predicting the second label, you're only looking at the second input representation to make that decision. So let's contrast that with a CRF. In a CRF, the picture looks similar, but I added a bunch of lines between these y variables. And in this case, let's say we still want to predict the second label. Our distribution would look something like this. Our model would be asked to predict the second label y2, still conditioned on the input x2, but also conditioned on the adjacent labels y1 and y3. So at this point, if you're familiar with CRFs, this should be fairly straightforward. If you're not familiar with CRFs, this should kind of seem a bit weird. Normally we think about, we have our input and then we predict our output from the input. Here we're presumably predicting this y2 label given the other outputs, but so basically it looks like we need y3 to predict y2, but presumably we'll also need y2 to predict y3. And so this seems weirdly cyclical, and that's kind of the magic of CRFs. It turns out that for cases like this, there is a very nice algorithm or set of algorithms you can use where you can define a distribution like this where all of your output variables depend on each other. And so long as you don't make these dependencies too weird, there's a couple of nice algorithms to work with this joint distribution of all the output variables. And you can find the mode of the distribution, you can sample from the distribution, do everything nicely, even though everything kind of depends on each other. And as long as there are no cycles in the dependencies. And so here we have a straight line of dependencies, but there's no loops, so we're good. And so that's pretty cool. And you might think, well, okay, CRFs are awesome. If y2 can depend on y3, but then y3 depends on y4, y4 can depend on y5, then in principle, y2 can depend all the way on y5, and everything can depend on everything else. And to an extent, that is true. Everything can depend on everything else with some caveats. And the caveat is this. Let's kind of pretend in a little thought experiment, we're going to take one of these labels, say y3, and we're going to fix it in place. We're going to say we know that the third input, the third token in our sequence receives this one particular label where we know that a priori. Now, if we fix this in place, we can ask, does everything still depend on everything else? Y2 still depends on y1 and y3, but y3 doesn't depend on anything anymore, it's fixed. And so by fixing y3, our chain ends. Y2 depends on its neighbors, but it can't depend on anything on the other side because y3 doesn't depend on anything. And so this is a property called conditional independence. what we can say. Sorry?
Right back in.
Wait, I can't hear what you're saying. Can you repeat that?
I was asking if I can butt in.
Yes, please.
So are you saying the dependence is always just to a distance of 1?
Not necessarily. So if we didn't fix y3, then y2 depends on y3, y3 depends on y4. They directly depend on their neighbors, but they can indirectly depend on their distant neighbors. And so if we don't fix this, we can have information about y5 that goes into the decision for y2. However, if somewhere in the line we fix it, we freeze one of these labels, then that information can no longer flow. Then we're only stuck. The information can only flow as far as this frozen label.
So the direct dependence is of depth 1.
One more time?
The direct dependence is only of distance 1.
Exactly. And
Thanks.
yeah, you could, and to be honest, you can draw your CRF differently. I'm working with linear chain CRFs that have a direct dependence of length 1. You can draw it differently to have different direct dependence graphs. But in this particular example, yes, the direct dependence is only to its direct neighbors. And so what we can say is that so y2 in general is not independent from y5, but y2 is conditionally dependent on y5 given y3. And so what that means very formally is in the whole joint distribution over labels, these are not necessarily independent. They might have some dependency. However, if we look at the conditional distribution over the conditional distribution of label sequences conditioned on any particular value for y3, then everything to the left of y3 has to be independent to everything to the right of y3. This is conditional independence. And I guess I have the word Markov assumption in the slide. This Markov assumption is this assumption that we only directly depend on our neighbors. And so linear chain CRFs are models that follow the Markov assumption, and they suffer from this conditional independence. So that's very theoretical. Let's go to a bit more practical applications. Let's talk about using a CRF model for semantic role labeling. This is a task from natural language processing, and it is a task of, given a sentence, answering who does what to whom in that sentence, or rather, given a sentence and given the what, finding the who and the whom. So we know this is the sentence, we know what the verb is, and we want to know what the doer is and what the doee is. I picked a German example just because it works well for this purpose. I'll give translations, don't worry. So this German sentence could be read to mean the cat chases the mouse. In that case, we would label the cat as the agent and the mouse as the patient. And here I've done that. Die Katze means the cat. That's labeled as the agent, and die Maus is the mouse that's labeled as a patient. And this is using BIO labels, which is, it's just a way of encoding these multi-word expressions as spans. So here we can take this task and express it as sequence labeling like this. And this would be the input, these would be the labels. Now I picked the sentence on purpose because it's a bit tricky. It's actually ambiguous in German, and it could also be read to mean the mouse chases the cat. Of course, if we take this reading, then we'd want to label the mouse as the agent and the cat as the patient. And so here, die Maus becomes the agent, and die Katze becomes the patient. Now, this actually, so because both of these are valid interpretations, we might expect that some semantic role labeling model should assign a high probability to both of these. However, if we're using a CRF, we run into a problem, because in both of these analyses, the middle token, the verb, receives this placeholder O label. That just means it's neither agent or patient. And because this is constant in both analyses, the Markov assumption and this conditional independence gives us a problem. Because this is constant, we know that everything to the left of it and everything to the right of it have to be independent from one another. And so if we allow for those two good analyses, the model will also have to assign high probability to these two nonsense analyses, one where we have an agent on the left and right, and one where we have both a patient on the left and right. And that's obviously not good. So not only is that, that's incorrect, those are not good analyses, we don't want our model to be wrong, but it's also, it's not just wrong, but it violates some a priori knowledge about the task, we have about the task. In particular, if you look at this task and you look at the task definition, you'll see that each predicate is supposed to have at most one agent and at most one patient. So even if I didn't speak German, I couldn't read the sentence, I would be able to know that these are wrong. And so that's, I mean, it's bad that it's wrong, but we can know that it's wrong without even looking at the input. So let's just kind of play around with this constraint for a second. We're going to call this a constraint on our task. And let's just play around. If we wanted to, we could come up with a regular expression that matches all input sequences that follow this constraint, and it doesn't match any input sequence that violates this constraint. That would look something like this. I mean, it's actually a little bit messy, and even here, the notation I'm using, it's messier if I use proper notation, but it's certainly possible. You could write a regular expression that would match every label sequence that follows this constraint and nothing else. And of course, if you can write a regular expression for that, we can make a finite state automaton that matches the same language. That would look something like this. It's a little bit less messy to me than the regular expression. It has some nice symmetry to it. It still has a lot of nodes. It's maybe a little bit tedious, but you could definitely write down an automaton. And if you go through this, you can convince yourself that basically it will accept all sorts of different strings, but any string that it accepts, it can't have more than one agent and it can't have more than one patient. So yeah, I mean, I've been playing around a bit. I've been making automata for no reason. Where am I going with this? I want to kind of back up a bit and look at this task at a meta level. So not specifically semantic role labeling, but this task of enforcing constraints on a CRF. What we have is we have some CRF describing some distribution over label sequences conditioned on input sequences. And we also have some non-deterministic finite automaton M, and it describes a regular language L that encodes this constraint that we know a priori and want to enforce in the output. And so what we want from there is we want to make a new constraint CRF model describing the distribution P of Y given X and L. That's a bit of an abusive notation on my part. What I mean by that is we want to take this already conditional distribution and we want to further conditionalize it on the condition that conditioned on the event that our label sequence is in this language L. Being very explicit now, what we mean is exactly this. So we want a new distribution that's proportional to our old distribution for every label sequence that's in our language, and where this new distribution should assign 0 probability mass to everything where the label sequence is not in our language, in our constraint language. So that's a kind of very high level problem statement. And if we have this, then we can use these CRF models and we can use a priori constraints on them, enforce a priori constraints on them. So now let's talk a bit about the construction. I'm going to talk about a high level plan, then get into a little bit of details. So the very high level plan is we want to make a new CRF whose label set is, instead of the set of labels, we're going to use the set of all of the arrows in our automaton as labels for this new CRF. And so the old CRF outputs sequences of labels. This new CRF will output sequences of arrows. We're going to play around with this new CRF's weights so that whenever it outputs a sequence of arrows, that sequence of arrows has to be contiguous. And so all the arrows have to point into each other. And they have to form accepting paths. So they have to start at the initial state and end at an accepting state. Once we do that, we can use a little bit of clever rate sharing to ensure that the unscaled probabilities for each path is equal to the unscaled probability for the corresponding string in our original CRF. And we'll show that that ends up giving us exactly the distribution that we are looking for. So I'm going to go into a bit more detail now, and first I'll focus on the automaton. There are just a couple different properties we want this automaton to have. So in the previous slide, we made this little implicit assumption that we can switch back and forth between strings in our language and paths in our automaton. In general, that's not necessarily true. A lot of times, especially with these non-deterministic automata, you'll have one string that might have many paths that correspond to it. And so we want this property that for each string, there's exactly one path. And it turns out this property has a name for automata that's, we want M to be an unambiguous automaton. So every accepting string has exactly one, every string in our language has exactly one accepting path. It turns out this is a little bit weaker than determinism. It's kind of, anyway, it gets a bit theoretical, but this is called an unambiguous automaton. And it turns out that all NFAs can be disambiguated. There's a nice algorithm to take an NFA and get an unambiguous NFA that's equivalent. And so we can make this assumption without, we can assume that M is unambiguous without any loss of generality. The second property we want is kind of just a little technicality. A CRF usually expects that the input length and the output length are the same, especially for sequence labeling. You want as many labels as you have input tokens. And so that means we can't have any epsilon or empty transitions in the automaton, because if you have an empty transition, then the lengths wouldn't match. I mean, that's even more true. Just like with the ambiguity, we can, if we have an automaton with these epsilon transitions, we can make an equivalent one without them. And that's actually very straightforward. So we can just assume we don't have any epsilon transitions. And finally, this is more of a soft constraint than a hard constraint. But if we're using a CRF and we're using the arrows in the automaton as labels, the training and inference algorithms for CRF are quadratic in the number of labels. And so if we have a lot of arrows in our CRF, then we're going to spend a whole lot of time doing training and inference. We want our automaton to have as few arrows or edges as possible. This is actually a problem I ran into, and then in trying to figure out how to minimize that, realized that this is one of these notoriously impossible problems in computer science. I think, so minimizing an automaton is minimizing an unambiguous automaton is piece-based complete, which is kind of a non-starter, and even having a provably good approximation to this is, I forget the complexity. It gets complicated, but it's very difficult. However, what we find is that for many of these tasks, either it's so small that we don't really care if it's theoretically minimal, or a lot of times the structure of the task makes it so that we can just look at the constraints and we can manually make an automaton that we know is minimal. So this is something to keep in mind, but a lot of times it's not an issue. So now let's talk about the CRF itself. We're going to get our hands dirty a little bit, just talking about the inside of a CRF. Hopefully it's not too overwhelming. So a CRF, let's see, it defines some distribution over label sequences conditioned on input sequences. We can say that capital Y is the set of all possible labels, capital X is the set of all possible input symbols, and we're describing some distribution P of Y given X, where Y and X are sequences of labels and symbols. It defines this as a very big product of this transition function and emission function. So here on the top, we have this equation. I mean, the main thing to look at is you're multiplying a whole bunch of things together. At the bottom, there's a diagram that encodes the same information. So X is our input symbol, X is our input sequence, all of the individual Ys are our output labels, and basically between every adjacent pair of outputs, we have a transition function. Between every output and the input, we have an emission function. And so the emission functions quantify how well the label matches the input. The transition functions quantify how well the adjacent labels go together next to each other. And if you multiply all of these things together, you don't get a probability, but you get an unscaled probability. So you multiply all these things in the boxes together, you get a big number. And if you divide by the sum of all of these things for every possible output sequence, you end up getting a probability. And so the probability is proportional to the product of everything in these boxes. I mean, the main point here, though, is that your probability comes out as a product of a bunch of things. And so if any one of these things is 0, the whole thing will collapse to 0. So hopefully that's not too complicated, but let's just march ahead. We're going to construct our new CRF now. So our plan was we have an original CRF. We want to make a new CRF that will then be able to interpret as this distribution that we want. This new CRF is going to have the same input space. It's going to have the same observation space, X, and so the inputs will be the same, but the output set, the label set will be different, and it will have a new transition function and an emission function. So the label set's different, the transition and emission functions are different, but the input set is the same, and importantly, the parameterization theta is the same. And what that means is if you have an old CRF parameterized by theta, you can use that theta to build your new CRF without introducing any new parameters. So let's just talk very briefly about how we're going to do this. The label set, like I hinted at before, the labels of the new CRF are going to be all of the arrows that were in our original, all of the arrows that were in our automaton. And so here, I don't have the automaton on the screen, it didn't fit, but these are just all of the little arrows we had, and each arrow starts at a state, it emits a symbol, and ends up at a different state. And so this would be the loop from Q1 to Q1 that outputs an O symbol, for example. And so we have the set of all of those arrows, that's our label set. Now the transition function, our strategy here is that because we want this new CRF to output a contiguous path through our automaton, we're going to pick our transition and emission functions to make sure that that happens. And this transition function is going to be responsible for making sure that the output is contiguous. And so what we're going to say is within our output sequence, we're going to have a bunch of these arrows. And for any two arrows, the transition function is going to look at the state where the first arrow ends and the state where the second arrow begins. And if they're the same, that means we had two arrows that pass through, we have two contiguous arrows that pass through the same state. And if they're the same, that's good. And so in that case, we just fall back to our original CRF's transition function for these symbols A and B here. However, if they're not the same, if this arrow goes into one state and the next arrow comes out at a different state, there's no way this could be a contiguous path. And our transition function will just return 0 here, and that will multiply with everything else and make sure that any sequence that has a non-contiguous link will receive 0 probability from this new CRF. And so our emission function is going to do something very similar, except our emission function will make sure that we start at the starting state of our automaton and that we end at an accepting state. And so basically, if we're at the first time step and the initial state isn't the starting state, we return 0. If we're at the last time step and the final state isn't an accepting state, we return 0. Otherwise, everything looks good. We're just going to fall back to our original CRF's emission function for this symbol A at this time step. And so what we can see is that if we don't violate any of these constraints about being contiguous or about starting at the beginning of the automaton or ending at a final state, if we don't violate any constraints, then everything we do here just falls back to the original transition and emission functions. And so this product will be exactly the same as what we had for the original CRF. However, if any of these constraints if any of these little constraints are violated and we don't end up with an accepting path, we end up with 0 probability. And so our new model will assign 0 probability mass to all of these all of these output sequences that aren't accepting paths. And it turns out that what we have is exactly what we want. So if we take an accepting path through the automaton, and we use this new CRF to count this. This shouldn't be a prime here, I'm sorry, this should just be a normal P, but that corresponds exactly to this conditionalized version of our CRF distribution where we want. It's proportional to the original CRF for all accepting paths, and it assigns 0 probability mass to everything that isn't in a string in our language. So that was a little bit, hopefully that wasn't a bit too detailed, but let's just move ahead for now. So now we have our construction, we have a new CRF that encodes this constraint distribution. Now we want to use it. So it turns out there's actually 2 possible ways we could use this new CRF. The way I've kind of been motivating it, it seems that I've been talking about we have an existing CRF and we want to enforce these constraints. And so one option would be we have an existing CRF, maybe we trained it on our model, and we want to use it at inference time now. And we can take our CRF and we can just enforce these constraints at inference time. And we're going to call that setting constraint decoding. The other possible setting is we could make a very new CRF. We just initialize it randomly. And then before we do any training, we construct this constraint CRF. And because the constraint CRF it's just another CRF with a different label set, we can train this new CRF directly instead of training the CRF and then constraining, we can first constrain the CRF and then train it with these constraints. And we're going to call this setting constraint training. And so I'm going to talk a little bit about comparing these two. First off, are these equivalent? And No, they're not. And second, which one should we prefer? And spoiler is that it turns out constrained training is the thing you want to do. So let's kind of compare these a little bit. So first off, I'm going to start with a very, very hand-wavy claim, and that's I'm going to claim that with a couple of caveats, constrained training should never do worse than constrained decoding. And there are a lot of caveats here, and don't complain if this doesn't hold all the time, but basically, if you're doing constrained training, you're looking directly at this constrained distribution, P of y given x and L, and you're directly trying to pick your parameter to minimize the loss or to maximize the likelihood of this constrained distribution. And so, I mean, you're maximizing it, so hopefully you'll end up with something that's better than everything else. On the other hand, when you're doing constrained decoding, you're not maximizing this distribution, you're maximizing this distribution P of y given x. And then after you've maximized that, you're then conditionalizing on L. And while conditionalizing on L will never hurt you, you're not guaranteed that what you'll end, I mean, this P of y given x and L will always be better than P of y given x, but you're not guaranteed that even if you found the global maximum during training, you're not guaranteed you'll end up with the global maximum of the constraint distribution. And we do a couple of simple experiments with some synthetic data to kind of demonstrate how that can be the case. And so the first experiment is we kind of constructed this to show that there can be arbitrarily big differences in likelihood between this constrained training and constrained decoding setting. And so we use synthetic data. We basically just constructed as simple an example as possible to demonstrate this. The input sequence is just always going to be constant. So we're not even learning, we're basically just learning the output sequence. The input sequence is always the same. We're going to say for the output sequence y, 75% of the time it's going to be AC, 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 AC repeated k times. And 25% of the time it's going to be BC, 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 BC repeated k times. We're going to say our language is this language of AC star, BC star. So either we have A's and C's in our language or B's and C's. We can never have A, B, and C all together in one string. And so basically this is our setting. And then for every K, we train and evaluate both the constrained training and the constrained decoding model. And so what we find is we get something like this. The green line is constrained training, and we see that on the left-hand side, this is just the probabilities of these two strings. And for constrained training, we see that this starts at 75%, and as k gets bigger and bigger, it says the model matches the data distribution exactly. It always assigns 75% of the probability mass to this ACK, and it assigns 25% of the probability mass to BCK. With constrained decoding, on the other hand, we see as k increases, it assigns more and more probability mass to this majority string and assigns less and less probability mass to the minority string. And it has to do with the fact that the way we construct these strings, every even indexed label is a C, and so you have a lot of these conditional, it has to do with these conditional independences. And the unconstrained, it gets a bit technical, but we can see that as k increases, constrained training is perfectly able to match it. Constrained decoding gets arbitrarily bad. And if we look at the negative log likelihood, we see that the constrained training setup, that pretty much just the log likelihood just stays at the data distribution entropy, while constrained decoding, as k gets bigger, the likelihood gets arbitrarily worse. So yeah, that's this. We have one more experiment to just kind of demonstrate that these two different regimes can differ in map inference. That means they can differ in which label sequence they think is the most likely given an input. Well, in this case, we still hold the input to be constant. We pick our data distribution to be a finite distribution over 3 possible strings. It's either ACD, BCD, or BCE with 40%, 30%, and 30% probability. The intuition here is that all of these strings have a C in the middle, so you have this conditional independence. And there's a majority for the prefix. That would be 2 of these strings start with B. And there's a majority for the suffix. 2 of the strings start with D. And Finally, we pick one of these strings to have a higher probability than the rest. We make sure that this string is different than the string that has the majority prefix and the majority suffix. And so we set our language to just be the finite language of exactly these three strings, and we train and evaluate both of the models. And so what we find is that here's a data distribution, and this last column is constrained training, and we find that when we train the model with these constraints, it just matches the data distribution exactly, or at least down to 2 decimal points. It learns it perfectly, and it can represent that exactly. However, the constrained decoding distribution ends up favoring the string with both the majority prefix and the majority suffix, because during training time, it has to model the prefix and the suffix independently because they're conditionally independent on this middle token. It ends up getting confused and it assigns most of its probability mass to this case where both the prefix and suffix are the majorities. So that's just kind of a demonstration that, I mean, the point of these two experiments is to show that there is a very big difference between constrained training and constrained decoding. And it seems that while both of these are probably better than not having any constraints, it seems that constrained training will give you will try to give you the correct distribution in these cases, while constrained decoding gives you some bad approximation of that that makes mistakes. So that was just talking about constrained training and decoding. I'm going to talk a little bit about some empirical experiments we did, and then I'll wrap things up. So this is all very theoretical. We tested our model empirically on the Ontonotes data set. And so the task we use is semantic role labeling. It's exactly the same task as all of the examples, but a bit more complicated. So the examples had 2 roles, agents and patients, and that was it. Here we have, in Ontonotes, there are 7 core role types, and there are 7 different types of roles, and these all have this property that they can only occur once per predicate. So they don't have to occur, but they can never occur more than once, just like agent and patient in our examples. We also have 21 non-core role types, which can occur as often or as infrequently as you like. You can have as many or fewer of them as you want in a sentence. You also have 19 continuation types. This just has to do with when you have a non-contiguous span, you have the role itself, and then later you might have a continuation role. And this can only occur if the main role occurred previously in the sentence. And you also have reference types, which I think they tend to be stuff like pronouns or stuff that refer to another noun phrase in the sentence. And these can occur in any sentence that has, there are these reference types, and they have to co-occur with the non-reference counterpart in the sentence. And so if there's an agent reference, it has to refer to some agent type in the sentence. And so this is a lot of different constraints, but in principle, I mean, you could write a regular language that encodes these exactly. I tried doing that, and it turns out that if you do that, you end up with a very, very, very large automaton. This is a very conservative lower bound on the number of states. It's something like 2 to the 2 times 3 to the power of 19. It's much bigger than I could fit in my computer. It has to do with all of these basically combinatorial. It has to do with the ordering. There's very free ordering. Anything can occur in any order, and your automaton has to account for all of these permutations, and it gets very big. And so that was kind of frustrating. We have these constraints to regular, but we can't fit them in our computer. However, we found that to make it, most of these role types are very rare. They occur very infrequently. And we can make a model that just doesn't know about them. And of course, at evaluation time, if it's supposed to predict this, it won't be able to, and it will not get as good recall as a model that could. But we find that so many of these are so rare that we can just ignore them, and it doesn't hurt us too bad. So what we found is what we do is we limit ourselves to 5 of these 7 core role types, and 17 of the, well, first off, we say the reference types, we don't care about their constraints, and then we take 17 non-core and reference types together, and we have 1 continuation type. And so we got rid of a lot of these role types, but we got rid of the very rare ones, so we hopefully don't hurt ourselves too much. That was a little bit about the data set. Now let's talk about the models. So all of our models are going to look very similar. We have a Roberta-based model with some kind of CRF used as the output layer. So for our baselines, we have just Roberta with a normal unconstrained CRF as the output layer. And in this case, because we don't have to make an automaton, it's unconstrained, we have the option of using all of the role types, including the ones we excluded. And so we have two variations of this model. One of them uses the full set of role types, including these rare ones. And the other one uses the same reduced set of role types that we're going to use for the constrained models, just for better comparison. The other models we have use this constrained CRF on top of Roberta. And in this case, we have two variations. We could either use the constrained decoding or constrained training if we want to enforce these constraints at training time or just at the decoding time. So that gives us four separate models. Now, here's a really big table of results. I think the first takeaway is that we get the best performance if we use a constrained CRF with our constrained training. We see as well that if we use constrained decoding, we get slightly but significantly worse results in the F-score. We see that if we use, any pattern you might expect, I think you find in here. This is very nice in that we found pretty much everything that we hypothesized shows nicely in the results. The constraints work better than the model without constraints. The full set of labels works better than the reduced set of labels. When we use the full set of labels, we see better recall. When we use the reduced set of labels, we see worse recall. Perhaps the only surprise is that the constrained training model is so good that even though it has the reduced set of labels, it ends up having a very close recall to the CRF that has the full set of labels. And it turns out there's no statistical significance between these two. So the constrained training, even though it's limited in how good it can do in recall because it can't predict everything, the constraints help it to end up tying with the basic CRF with the full set of labels. And otherwise, I think it turned out that this was state of the art when we published it. I think since we published, there have been a lot of people doing a little bit better than this. But yeah, to be honest, so the state of the art seemed to be mostly, like even our baseline model beat state of the art. So it seemed Roberta was the main thing that pushed us above state of the art. And then the constraints, of course, help on top of that to give us the best model. But that's what the results look like. And it's actually quite nice. It backs up what we expected. The empirical results kind of mimic exactly what we expected theoretically. So finally, I have a little bit of self-promotion. Our implementation is available as a Python library, and you can use it pretty much as a drop-in replacement for a standard CRF in any PyTorch project. Like I said, you can use it as a drop-in replacement. You can install it just like this, pip install CCRF, and also in the chat, I think Dimitri posted a link that leads to a GitHub link that will, you'll be able to see some code of this space. It's not fully documented, but it's well commented, and there's a lot of examples of how to use it on GitHub. So I definitely invite you to try to use this yourself in your own projects. And yeah, so that's what I have. And now I guess I'll open the floor to questions.
Thank you, that was really nice.
Mm-hmm.
I have one question.
Yep.
If you could go back to you were talking about removing some of the constraints. You had these 17 types of something. You might want to make that full screen. Okay. So you took the automaton, if I understand correctly, as defining the set of possibilities. Like if intuitively that was the point of it. It was a sort of, I'm removing everything and now I'm giving you back like what you're allowed to do. But maybe I'm phrasing myself strangely. What I wanted to say is, what if instead of removing a few of the reference types, continuation types to make it smaller, you simply removed the constraints on them? So they would still be there, but you consider allowing like multiple of this type that you don't want to have too many states for.
No, so that's actually a very good point, and so I kind of sweep it under the rug here, but I kind of do both of these things.
Oh,
So basically, in the automaton we end up with, in some ways it overgenerates, in some ways it undergenerates. And what I mean by that is it undergenerates in that if there's a sentence that has these very rare roles, it won't be able to generate those. Those are outside of the language, and so in that way it undergenerates. On the other hand, I have all of these constraints, and among these, I basically say reference types, I'm ignoring this constraint that they have to co-occur with their non-reference counterparts. I found that just for practicality reasons, it made sense to take these reference types and treat them just as if they're normal things that can occur whenever they want. And so in that case, it overgenerates because this model could generate a label sequence with the reference type without having the corresponding reference type, and that would not be allowed. And so, no, it's actually a very good question. And yeah, in principle, of course, if you can encode your constraints exactly, you can do it. But if you can't, you have the option of both over and under generalizing. And I guess one will affect precision, one will affect recall.
cool, thanks. So it's a sort of art.
Mm-hmm. Yeah. I mean, I guess, yeah, the empirical stage of it definitely becomes a bit of an art, trying to make as good of an automaton as you can that fits in memory and can actually be practical.
Great.
But I think,
Yeah, you have two hands up.
I see Alex first on my screen, so I'm going to, so Alex?
Oh, hi. Yeah, really interesting stuff. I had kind of a theoretic question. So it's like the blow up in the size of the automaton, is that caused by the intersection of the disambiguation algorithm?
So I never actually, okay, so I did implement this disambiguation, I implemented the disambiguation algorithm, and I was going to do that, and I found that that just ended up not working. So at the end of the day, I constructed this by hand. I think, I mean, the core of your question is, would it still blow up if it didn't have to be disambiguous? And my impression is that it would still blow up. And the reason for that is at any point in time, you have to remember which roles you've seen and which ones you haven't.
Right.
And of course, that's 2 to the power, if you have k roles, that's 2 to the power of k. And at a lower bound, you need 2 to the power of k states to remember that.
Yeah. So it's because you're intersecting a whole bunch of different constraints. Okay, I guess my other question was like, if you're in a situation where the ambiguity is an issue, right, where the cause a blow up in the automaton, then presumably you can like work with the ambiguous automaton. I think the mode of the distribution is going to involve summing over all the paths that are equivalent. And so, I mean, so you're sort of tiptoeing between 2 different problems, and I was just understanding if I kind of understood the sort of landscape of the problem correctly.
No, so this problem of summing over all of the paths turns out, this is horribly intractable. This is one of these very, you look at the math for it and you just decide it's not possible. I think there are some approximations to that that other literature has done, but it ends up being just an approximation. And I found other literature, sometimes they'll just say, well, we know this is ambiguous, but for each string, we're gonna just somehow arbitrarily decide on one canonical path for that string, and we're gonna treat that as the right answer and everything else is wrong. And in some contexts that seems, or at least some authors have read report that seems to work well, but of course it's also just it's an approximation.
Yeah, and I guess one of the points of the CRF algorithm is you've got the sort of, it's kind of a convex problem. You don't want to sort of with your nasty approximations. So it's nice.
Yes, exactly. Okay, so I guess Marco, you have your hand raised.
Yeah, thanks for the nice talk. And yeah, the thing I was going to add about the over generating and under generating is like the more general thing that you can do, like hyper minimization. Do you know what I mean? Have you heard of that?
No, I haven't. Elaborate.
It's like you can form an automaton that has some substantially lower amount of states but it accepts a certain amount of words per length that aren't actually in the language, but it doesn't reject any words that are in the language. And like you can form them quickly, although you can form them quickly and there's like space bounds and things like that. But the one thing that I wasn't sure about is that I don't know that you can form them quickly without first just building the automaton and then hyperminimizing it. I don't know if you can like do it from a implicit representation, but that's another thing that could be done if you're okay with over generating.
No, that's actually a very interesting direction. I wasn't aware of that word hyperminimization. That's something I'm definitely going to look up because it sounds relevant. And I know this is something that we never ended up doing any work on it, but we'd considered that maybe we could take constraints that aren't regular, for example, some context-free constraint, and then we could find some regular approximation that overgenerates but still encompass. Yeah, but I mean, we've kind of thought of this idea, but I guess I didn't have the vocabulary for it. So, no, that's a really good idea, though. Thank you.
Yeah, I'll post a link or something in the chat.
Thank you.